Okay, sorry about that. I lost you. I moved the machine and I somehow got disconnected. So from the app, not from anything else. So I wanted to write some things down, so I need to share my screen. And then we get these. Okay, and I go to OneNote. This one here. Okay. Can you see that? Can you see the OneNote? Okay, thanks. Okay, so let's get a new section. Okay, so let's talk about an agenda a little bit. So we had the issue of the exercise 1, and I guess maybe that's what. So let's do a poll, and then we will set the order of questions. I'm just a little bit annoyed about the noise outside, and I have to learn to live with it. And let me shut off the video. Okay, and do the poll. So what choices do we have? We have the choices of 2 exercises, 2 problems, and the previous assignment. So we have 5 choices. And it's basically to get your priorities. So 1 and 2 are exercise 1 and 2, 3 and 4 are problem 1 and 2, and 5 is assignment of day 6. The noise has subsided. I don't think you can see the score until I say show responses. Is that right? Oh yeah, you don't see anything. Oh yes, you do. Oh, you see the choices as we're making them, correct? Yeah, okay. Because you're fair enough. So you see what's going on. Hey, we got no response down to 8. Oh, because you're seeing my screen. Now I get it. Okay. All right, a little slow on that. Okay. Okay, I think back to here. So basically what it is, we'll do problem 1, problem 2, the assignment, and then we'll go to the exercises. Okay, that sounds like a good choice. Now you can see your responses on your own screen. Okay. So problem 1, problem 2. Okay, so we do B1, B2, assignment 6, X1, X2. Okay, now we know where we are. I guess when we do these exercises, we'll get to the technical stuff that we were talking about this morning. Okay, so let's do P1. Let's turn to the right page. The following table shows the inside diameter of a shaft measured every hour for 30 hours. These observations were drawn at random from a normal distribution with mean 9.75 and standard deviation 1. Okay, setup. Okay, what this is saying is that the person is acknowledging that this was not real data, that they generate this artificially. Okay, and set up an UMA control chart with lambda equal 0.1 and L equal 2.814. And so we can either do that with Excel on our own, or we can be lazy and just do it with Minitab. And I'm going to be lazy and I'm going to do it with Minitab. Now we reserve the right to ask you to do these things with Excel, if we don't think it's too bad. So this is data that I should find in Excel. Probably I have to go back to the, back to here to collaborate and get the, because I think this data was just added to the data here, to the file, okay, to this Excel file for exercise and problems. And if I look at that, I download it, I open it, and Excel. Okay, here we are. Hey, it opened up on the right place. So this was wherever it was. I take this, let me check 945. So we take that Control C. We go to Minitab. I'm going to open up Minitab. Don't see it here. Got to go down. Minitab. 18. Okay, I go here and I deposit the data. So I've got it at C1. I go to Stat, Quality Tools, Control Chart, sorry. Go to Time Weighted Charts, which the UMA is. I go to UMA. And I need to go in here and just add that data. Subgroup size. Now let me look at this. Following table shows the insight diameter, the observations. So it looks like each one is an observation on its own, so it's 1. And then the weight of the UMA, it's telling me to use 0.1. And then the L. So where the heck do I find the L? Okay, so we go to UMA options. Oh, yes, that's a reminder that the mean, it doesn't have to be extracted from the data. We can say 9.75. And the standard deviation is 1. Oops. And that appeared, that the window is not appearing all the time. Isn't that wonderful? Okay, and that's good. And there must be something else where I can get my L put in. It's probably under limits. Multiple standard deviation, that's L. So what does it use? Okay, my suspicion is that it uses 3. 2.814. And we'll see what happens. Whoa, yes. So I don't believe that this, I don't believe the person who made us this problem is that the observations were drawn at random. Because all of a sudden, if they would have been drawn purely at random, we wouldn't have observed the ones at the end. So I think what happened is that generated 25 and then decided to up the others just to make this good. Now, let's look at this. I still don't have a pointer, which is, oh, wait a second, my arrow. Yes, here's my pointer. I can probably make my mouse bigger. Anyway, doesn't matter. So look what's happening here. It has a UCL 10.438, but then it has also a 2.8 standard deviation at 10.395. So we can then say, in this particular case, it didn't really matter because these blue points here would be within bounds either way. So we don't have any points in between. But it may make a difference sometime, and you can. It has a default of 3. I believe that if I were to go back and set the stat, go to control charts, and repeat what I just did with the UMA, except set the UMA options for the limit at 3, specify 3. that it would only produce 1. Let's check that out. Yeah, so everything gets written on top of itself. Just minimize that so that we can see. Yeah, everything gets written on top of itself because it's overriding its default. So nobody would ever pick a 3, and they said, well, if you do that, you deserve what you get because this is for selecting an alternate L other than 3. So if people don't know what they're doing and they're just going along their merry way, then they would not. Then they would get a 3, which isn't necessarily what they want to get the desired ARL naught of whatever. There is no mention here. Just pick your lambda and your L, and we're done. I think when we do problem 2, we're going to be dealing with this issue. Okay. So is the UMA chart detecting any shift in the mean considering the given data? Yes, it is. At 26, sample 26 is out of bounds, and that's that. Any question on this, what we've done so far? Nope, so we go on. Let's look at the problem 2. For doing problem 2, what is an in-control average run length? I mean, you might say, is he looking for the definition of an ARL? In control, ARL not? Is that not 370? But it's not. Oh, that's what they want to know. They want to know what is the quantitative value of ARL not for this problem. And you might say, well, how am I supposed to know? Okay, well, you're supposed to remember that there is a table, which I have prepared here. It's a table from the textbook, and it's our table that relates lambda and L to the ARLs. Okay, so it's the average run lengths for several UMA control schemes, and where we are is we are right now at the combination of 0.1 and 2.814. Aren't we lucky? So they picked this because they wanted to have a particular. They wanted to have a particular characteristic. And so what's the ARL, folks? 500, thank you. What's the second question, which is what is ARL for detecting a shift of 1 standard deviation in the mean? Thank you. And we're done. Okay. So it's just an awareness that you now, just to let you know, my preference is not to specify L and lambda, but to give you this table and then to provide some kind of what kind of a shift in mean you want to, and then you go along here and you find out what the best combination of L and lambda is. That would give you the lowest ARL1. The ARL naught is always 500 here, and that's that. So I've done problem 1 and problem 2. It's 420 and moving right along. But I might need a lot of time for assignment 6. So any questions on this? How to guarantee mean shift is 0? Okay. Where can, oh, okay. Going back to where can we find the table? The table will be provided. So the table there is a source on the exam. If you need this table, there is a source folder that has, in addition to the formulas that we've posted, you know, that standard formulas that's been on the web since day one on the references. Now this table will also be there, so you'll be able to access it from there. Okay, you get it from the book, but we'll give you a copy if you need it on the exam. How to guarantee mean shift is 0 AR5? Okay, no. There's no. If the process, the 0 row is telling you that that's the ARL naught, that the mean hasn't shifted. The process is in control, which means the mean is exactly where it was. And if the mean is exactly where it was and the process is in control, and you can expect a false alarm every 500 days, just like we used to have, you know, this is a particular alpha. It will be an alpha which is smaller than 0.0027. So the type 1 error will be smaller because our ARL here is larger. That's That's the information that's being provided on this table. That the first row is the ARL naught because the mean has not shifted. If the mean has shifted, then let's say by 0.25, it will take on average, with this particular combination of L and lambda, it will take on average 106 samples before you can detect that small change. If you were looking at a 0.5 of standard deviation, it'll be less. And as the shift grows, you'll find out sooner and sooner. If it's 4, you'll find out after 2.2 on average, after 2 or 3 samples. Okay, so that's what this is saying. If I answered your question, how to guarantee Xuki, Ma? Does that answer it? Okay. Gurinder, where does the 10.3 come from? It's on that table. How is it calculated? That's a secret. That's something that we don't cover in this course. Is shift in mean calculated the same as Q? So no, shift in mean is not calculated. Shift of mean is an input. Now, if the mean is not shifted, then that's that. If the mean is shifted, so this is an input to this table, and the output is the body of the table. Okay. Is shift in mean calculated the same as Q? So no. Yeah, shift in mean is the same. You're trying to detect a small change in the process, so we're talking the same way. It's the same lingo in UMA, in QSUM, in Shewhart. We're always talking about trying to detect a shift. Okay, now we didn't talk about it that much in the Shewhart chart. Found out is it in control or out of control. But we did say generally that those Shewhart charts are not good at detecting less than 1.5 standard deviations. Once you get it to less than 1.5 standard deviations, then you need these Shuma and QSUM charts. Can we see the formula and reference for the final before final? We see the formula and reference. Okay, I don't understand the question, but I think I know what you mean. The answer is no. In other words, can I show you the formulas that you will be needing on the exam before the exam? So I have a choice. I can either show you all the formulas that we used in this course, and then say one of these formulas will be used, which is kind of useless, or I can give you the formulas that will be used in the exam. I might as well give you the questions. Hello, Dr. Francis. Oh, Paul, I'm busy right now. Can I call you back? Yeah, Tuesday. Okay, I'll be there. Okay, bye. Yeah, sorry about that. I do take the phone because it's important. I don't get that many phone calls. Okay, where was I? Yeah, I can't. If I show you I don't like to show the formulas that you need because then you can refer to questions. Okay. So we will give you the formulas that you need. At the end of the test, there'll be a bunch of formulas. And I'm not going to trick you and give you formulas that you don't need, okay? If you need them, they're there. That's that. So Wenking Wang, did I get your question right? Okay. I think she meant, can you show us the formula that will be provided to us during exam? Yeah, that's what I said. That's what I explained that I cannot, because I'm giving you the questions. So I'll give you, so that's that. Yangte, can we know what kind of references will we have before the exam, just in case? That's the same question, I think. Is 500 is false alarm right? Yes, so 500 is a false alarm, correct. So if the mean has not shifted, but you can expect that you can wait 500 samples before the process goes out of, it falsely reports that you're out of control. Okay, that's correct. Ignore my question. I think she meant, can you show that when can, yes, okay, we're done. Okay, so I did problem 1 and problem 2. Now, as the moment has come that we have to do A6. Okay. This was not an easy problem. Okay, this was not an easy problem, I must admit. Okay, so what we are talking about is day 6 assignment. Now, it wasn't a disaster because what happened was you assumed that a normal approximation to the problem, to the binomial, will fix the problem. The unfortunate thing is that you cannot assume that off the bat. So you need to look some up under what conditions. But in this problem, we're not going to assume that the normal is a good approximation. Just want to find my notes here. I'm trying to do this problem. Okay. So one of the things well, let's look at the problem for a moment. A sample is taken every hour for a manufacturing process to check for defective items. Now, a sample, which means a sample, I don't know what size. Under in-control conditions, the process is known to generate 1% defective items. So I can say right away, jump to the conclusion that P naught, this is the percentage in the binomial process, will be 0.01. Okay. However, the proportion of defective shifts to 3%. Okay, so if it's 0.03, it shifts out of control. When the process goes out of control, design an appropriate control chart satisfying the following requirements. The probability of false alarm is 0.004. So therefore, my little table here, which I would like to have as like a blanket, alpha 1 minus alpha, beta 1 minus beta. This is in and out control, and this is out and in bounds. So alpha is the probability that it's out of bounds, but it's still in control. So it will be a false alarm. The probability of a false alarm is 0.004, and for the record, ARL is equal to 1 over 0.004. I'm not sure this is going to help me, but what the heck? I think this is 250. Okay, fine. When the shift occurs, it is detected on average at the third sample following the shift occurrence. So on average. So what it's telling me that on average, so this is one condition, right? And then the other condition is that the shift occurs, it's detected on the third. That means my ARL 1 is equal to 3. And therefore, I can infer that since ARL 1 is equal to 1 over 1 minus beta, which is equal to 3, therefore, this is the same as, I'm on this side here, 1 is equal to 3 minus 3 beta, beta equals 2/3. 0.666, whatever, 7. Okay. So I've got an alpha, and I've got a beta, and I've got an ARL1, and I've got an ARL naught. And now what am I supposed to do? Control chart design requires finding the minimum sample size as well as the corresponding control limits. So I don't know N, I don't know the UCL, I don't know the LCL, and I don't know the sample size. And I'm supposed to make sense out of this. Okay. Well, we know that, I'm just shuttling here, that the number of defectives, if it lies between UCL and LCL, that'll be equal to 1 minus alpha, right? That'll be 0.996. And there's also a probability then, now if you, normally when we do the normal approximation, we had something like that, and then we had, this was alpha over 2, and this was alpha over 2, right? So it was an equal chance that you were high and low. So therefore we can say that the probability that D is greater or equal to LCL is equal to what? Is alpha over 2, which is 0.002. And we don't know the LCL, we don't know the UCL. But wait a second. What can we do with this? We can do something with this. No, sorry, this is wrong. This is, made a mistake here. Okay, so now I'm looking at this diagram here, and there's a probability that it will be less than LCL or less than or equal to, I don't know, it's discrete, but let's leave it that way. Probability D is less than LCL is equal to alpha over 2.002. Are you okay with that? Is that okay? Anybody? Yeah, you're okay with that? Okay, we're okay with this. Okay, and also the probability that D is greater or equal to UCL is equal to alpha over 2 also. And also equal to 0.002. Well. We don't know what N is. Okay, so the way we're going to do this, folks, is we are going to guess an N value, because otherwise without N we can't do anything. And let's say N is equal to 100. Just, I don't know, you can make up anything. So guess an initial N value. We're okay with that. Now there is let's start with the LCL. There's a probability that D is less than or equal to LCL, and by the way, given P naught, which is 0.01, this is a binomial, right? So I now have an N, I have a P naught, and this is supposed to be equal to 0.002. Do you know a function in Excel that might help me determine the LCL? Anybody? If you know the binomial distribution gives you the binomial distribution. The inverse. The inverse not norm, not the inverse norm. No, not goal-seek, not yet. The inverse binomial. Right. So the binomial disk, it takes you from an X to a probability, right? And the binomial, I think it's binomial inverse. I think that's what it is. It takes you from a probability to an X. Well, that would help, because I can then use binomial inverse to do that. So let's think of that. Let's not do it yet, but we're thinking out how to do this problem before we go to the computer. Okay, and if we do that, I can also, so I will have a probability of X. I can also, so that, what will that give me? What will binomial inverse then give me? So I'm going to have binomial.inv, and I think we need to look at this a moment. I need to look at let's say file new. I need a sheet. No, come on, folks. Yeah, here. Why doesn't it appear? Oh, there we go. Okay, I need a keyboard. Sorry. I hope I don't hit a button and disconnect. All right. So if I am here and I want to see the binomial. I want to see this guy. Binomial inverse. Here's a binomial inverse, and it asks me for N. It asks me for the probability. Now let's see it's what it's all about. Okay, the trials, the probability, the alpha required the criterion value, that returns the smallest value for which a cumulative binomial distribution is greater than or equal to a criterion value. and the criterion value is alpha. So that's exactly what we need, because when we look here, we see here that we would want. So what does it want again? It wants the oh, where was the help? Hold on a second. Where was the help? No, not here. Ah, I'm gone. Where was I? Here. Drive you nuts. Okay. It wants trials. That's n. It wants p naught. And the alpha is the probability on the other side. So we want here, let's get back to this guy here, binomial inverse trials will be n, that's 100, and the probability will be 0.01. Sorry for the lousy writing. And the probability here will be 0.002, right? Oh, over, yes, alpha over 2. Yeah, so what's the probability that it will be 0.002? That's what we want, and that will give us, what will that give us then? What will this will give us a number, but what does the number represent? What does the number, look at this, this says the probability being less than or equal to LCL given P naught is 0.002. This binomial inverse says, if you give me n, which is the trials, you give me the probability, and you give me this thing, what will it solve for? LCL. Thank you. No, not the mean. LCL. It will solve for this. What is the value of LCL on this side? It could be X. It could be anything. What is the value of this here? Which, you see that circling that I'm doing? No. What is the value here that this guy here, this will be LCL. So I can solve for LCL based on an n, okay? So the way we're going to do this is we start with an n, we get an initial LCL. Then, I'm going back to writing now. Again, hope nothing gets falls apart here. Okay. Sorry. And then I'm going to go probability. Now, what's the other probability? Probability D greater or equal to UCL, given P naught, has to be also 0.002, but I don't have an inverse function that deals with the greater than or equal sign, so then it's 1 minus the probability that D is less than or equal to UCL given P naught, and I'm using my less than or equals and a little bit sloppily, but hopefully that'll be fine, 0.002, which means that moving a little bit up, the probability that D is less than or equal to UCL given P naught is equal to what? Equal to 0.998. Thank you. 0.998. And now I do the same thing. I do binomial inverse. I do 100 because that's the one I'm working with. I do 0.01 because that's what I'm working with. And now it's 0.998. And this is going to give me I'm begging you guys, but I just want to see an answer. A UCL. Thank you for humoring me. Okay, this is going to give me a UCL. So now I have an LCL and a UCL. Okay, now for now it tells me something about beta. So I've got a UCL and an LCL that satisfies the alpha side of the house with a given n. Let's find out what our beta will be. Well, beta is equal to the probability that D, which is the number of defects, will be between the LCL and the UCL, given what? Given, that's beta is an error. Yeah, that it will be within the limits, that'll still be within the limits, even though there's been a shift and the mean is now P1 and it's 0.03. I can calculate that, okay? Well, that will give me three possibilities. It'll either be greater than 2/3, equal to 2/3, or less than 2/3. If it's greater, if my beta, my type 2 error, is greater than 2/3, what do I need to do with n? My error, my type 2 error is really bad. I want to do something about it. How can I decrease the type 2 error? How do I increase the sample size? Increase size. So therefore, increase n. And if it's equal to 2/3, I'm done. And if it's less than 2/3, then it's too good. Too good. So reduce, decrease, reduce sample size. Because I want the smallest one. And then you go ring around the rosy to that guy there and that guy there. And you go ring around the rosy. Now you might say, okay, this is all fine and dandy. Am I supposed to program this in Java or something? No, we can do this in Excel. We can do this in Excel. I wish, you know what I wish I could do, and I think I can do it. And then I say Control C. Is that what I have to do? Yes, I want to copy that. I want to copy this. I think I have to. I do a Control C on this picture, and then I go in here. Now let's see if this works. Control V. Wow. No, there was some way of doing this. Lasso. No, that's not good. Lasso. I'm fooling around, guys. Okay, and then I go Control, I copy, and then I go into here, and I say Control V. No, somehow it. Oh, I have to save it as. I have to do something that I didn't do. I don't know. Now I'm frustrated that I can't do this. Because I used to do this all the time. If you notice that in the videos, I cut and paste from. So let me see what this allows me to do. Oh, I know what it is. You paste it as a picture. That's my problem. I needed to paste it as a picture. So here you go. Oh, okay. Let's go. You guys are gonna fire me. Okay, I give up. Okay, I'm gonna go here and I'm just gonna do it. Okay. You can try pasting a picture on the left top of Excel. Yeah, I think I know, but I don't know. Now I'm getting. Oh, I need a keyboard. And I just go to a new sheet. I don't seem to have my control here. I just want to, I don't know how I close this. Sorry about that. I'm a little stuck, and I'm sorry. Nothing is working for me here. My mouse is not acting up. Help. Just close this. Oh, I can't close because this is not fixed. If I say Control Z, Control Z, Control Z, just keep on going back. No, that doesn't help. Try in another sheet. Yeah, I can't get the, you've entered too few arguments for this function. Okay. I really messed up and you entered too few arguments. File, close. I can't do anything. I'm stuck and I don't know what to do. Alt F4. Okay, let's try that. Alt F4. Control Alt Delete. That's what I tried. That was my first sense. Control Alt Delete. We should do this. I'm wondering if it's because I'm sharing, but I don't want to. I don't think that's the case. Click on function and clear. Click on function and clear. Delete. Delete. No. What the problem is? It's okay. Control Alt Delete. Yeah, Joanna. The problem is I don't have my mouse. I have my finger, but I don't have like my. Okay. Okay. Tell me again. I see G8 now. It's highlighted. Oh, I see it. Okay. I seem to have regained some measure of. Yeah, it looks like I'm it's getting better. At least I have control. At least it's something is happening. Yeah, I got my mouse back. Oh, okay. Delete. We're starting a new site. Okay, thank you. I'm back. Okay, so what I'm going to do is I'm going to sort of go from memory from what we had before. We needed an n, so I'm going to put the name of the variable over here, and that's 100. Okay, we'll need alpha at some point, and that's equal to 0.004. We'll need p naught at some point, and that's equal to 0.01. Okay. Now, at this point, we can calculate. We're going to need a UCL and an LCL. Let's start with the LCL. What we said is we're going to go binomial dot inverse. Somehow this isn't recognizing it. By now it should. Oh yeah, here we go. So trials is B1, and probability is B naught, and B naught. That's this guy. B3, and alpha is alpha over 2. So it's this guy divided by 2. And that's 0. So the LCL is 0 right now. And that's fine. I'm willing to live with that. And the UCL is equal to binomial inverse, sorry, and it's again 100, and it's p naught, and this one was 1 minus b2 over 2. That was a 0.998 if you remember. Okay, and it's giving me a UCL of 5. Okay. Now I need to calculate what beta is. Oops. So beta, well, beta P1. So that's going to be 1. And P1 is 0.03. And I don't think there's any other parameter. Now my beta will be the probability. So that's the probability that will be between my UCL and my LCL. So that'll be binomial distribution. Like that's just the probability that I'm between the upper control limit, which is this guy here. The upper control. Oh, there's no. Sorry, there's no. Forgot the equal sign. Okay. So now here. So here will be the number, which is the UCL. Trials is 100. Probability is what? Somebody? What should be the probability? 0.003, which is this guy here. And it's cumulative, so that's my standard. And I subtract from that the binomial distribution for the same number of trials. And, no, sorry, wrong mistake. For the LCL, which is 0, but I'm putting it in there because I'm going to be changing my n, and who knows what's going to happen to the number of trials, to the UCL. The LCL might not always be 0. So, and then the probability, which is 0.003, and a 1, and 0.87161. So where does n have to go? It's too high, so I got to increase my n. Now, right? What do I have to do to my n? Increase it. Okay. Yeah. Okay. Now, how can I use goal-seek? I can use goal-seek because I want this beta to be equal to 0.67, right? That's what I said it needed to be, right? And remember we said it's 0.67. We wrote that in the notes here. 2/3. Okay. So what we've done is we have a value of n, we've done this, we've done that, we've done beta. And instead of doing it manually, let's try to see whether we can use Excel goal-seek for this. And for that we go to data, and we go to what if analysis, and we go to goal-seek. And what do I do with goal-seek? Which is the set cell? Which is the set cell? Yes, thank you. Equal to this guy here, that's a set cell, and we want to set that equal to 0.6667, and we want to change the sample size, if I ever can get, okay, we want to change the sample size, and let's see how smart this guy is. Yay! Hey! So we have n is equal to 250. We have the lower control limit is 0. The upper control limit is 8. We have designed it. We have solved problem. We have solved the assignment. Yeah. That's it, folks. Mission impossible. Any questions? I know this was maybe unexpected that we would do this, but if you want to get it right now, to be strictly correct, some of these it could be that some of no, I think this is fine. So the lowest number of n that you need to have is you need to have n 250 sample size. And we've done problem 2. So we have 5 minutes to go back to exercise 2 and exercise 1. What is normal? Okay, that's a very good question. When is the normal approximation to binomial good? If you look at it, if you look online and just Google that, you'll find a variety of answers and very complicated rules between n and p. I think, to be fair, I think this exercise, this problem should have stated explicitly, do not use a normal approximation. But then I think that might have been, then it might have been a really hard problem. Whereas the way it went, you got it more or less right. By the way, what kind of sample size did you guys get? Does anybody remember? It's a few days ago. 87, 86, 80. Oh, that's interesting. So the normal approximation gives you 86, 87. That is very interesting. Whereas what you really need is 250. Aha. Okay. So obviously, in this case, by the calculations, you didn't do very well with that normal approximation. And that's a big lesson. That's a big lesson, because if we very often use it, we use convenient assumptions, like normal approximations to everything, and we make life easy, and we forget that sometimes it can take you down the wrong path. So that's that. XD, I'm not sure, but all right. Exercise 1. Let's see what exercise 1 was. Do CL? Oh, this is our discussion. Yes, do CL and LCL. Okay, so there's it's a simple explanation here, not very sophisticated. What we did in Excel. This has to do with QSIM, right? What we did in Excel and what Minitab does is we showed CI plus and CI minus to be positive. And what Minitab shows, it shows CI plus as positive and CI minus as negative numbers. Okay, so you'll see here that for Excel, the way we did it is that both of them, that LCL and UCL, sorry, that you only have a UCL, which is at H, and that both, and then things vary along here, and then you have another, the CI plus and the CI minus goes, usually this one's low and that one's high, stuff like that. And that's the way we did it. Here, the way Minitab does it is it shows this, it has an H there, it has an H here, and then it shows one on the positive side, and then it shows the ones on the negative side here. Well, this is probably not right, because when one is positive, one is negative. So that's the difference. So if you assumed this version of it, which was the version in the lecture, in the lecture video, then it said that CL equals LCL equals 0. Okay, but if you didn't, then here CL in the Minitab CL is 0, but the LCL is equal to the minus the UCL, all right, because they'll both be equal. All right, that's that. Is that okay for Q1? We talked about this. Are we ever going to be asked specifically for a UMA or QSIM chart using Excel when we always have the choice of using Minitab? I want you to think. Okay, let's put it this way. For QSIM, it's quite, when n is greater than 1, it's really, let me be honest, you can use Minitab, okay? So I was tempted to ask you to do it with Excel, UMA with Excel, but I think we'll just let you do it with Minitab, okay? And we'll ask the questions. The questions will become a little bit more sophisticated, like, not like this, but we have to become more inventive in order to not have everything be very straightforward. Okay, so Kishan, I think I've answered your question. Brenda Lee, so LCL is dependent on sample size. If we assume the Minitab form, LCL is dependent on sample size. No, it's just the difference between the Excel and the Minitab is just how it's the display. On one side, they're both displayed on one side of 0, and the other one they're displayed on the positive is above and the negative is below. Brenda, is that clear? LCL is dependent on sample size. Oh, well, everything is dependent on sample size. If you remember, you have to divide sigma over root n. That comes into play. So it doesn't matter. The Minitab form of the Excel form never make any substantive difference. You should get the same thing just by flipping one to be positive, so you should be able to recreate exactly Minitab. So Brenda, but LCL is equal to minus UCL H sigma squared over n. Oh yeah, H is always, but this H, this is minus H, and this is plus H, right? this doesn't exist. This is 0, right? So this is 0. This is minus h and plus h. And yeah, capital H depends on the square root of n, yes. But it's just that since plus h is equal to minus h, these two graphs are exactly the same. It's just in this case, you only have to draw one. Okay, it's just a matter of naming. Brenda, are we okay? It is an LCL. It's just they call that an LCL. See, if you portray both on top of 0, then you have one H. If you portray one on top and one on the bottom, then you need an H for the top and you need a minus H for the bottom. And yes, the LCL will be minus H, which is what I said. And so the LCL will be minus H, all right? And the UCL is H. I think we're okay. I mean, I don't think there's any more. Okay. Yes, thank you. If we do UMA or QSUM on standard deviation, we should have to use Excel, right? Yes. So that's a good cue, Kim. We are not. Yes, that is true. If you wanted to do a UMA and QSUM on variability out in workplace, I don't know if there's any software. I don't know of any software. Not that I'm the greatest expert in knowing all the softwares, but I know Minitab, which has a lot of control charts, does not have the QSUM and UMA for variability. So you would have to do it yourself. It's not a big deal, but you would have to use it yourself. Correct. Isn't the limits independent of n regardless? No, H, capital H is dependent on n. And capital H is K little h. K little h comes from a table, and that table usually requires you to provide. It's where you pick up your tables from. Correct. That is correct. That's correct. Now, hold on a second. This is sigma square root. The capital H is K times little h. Brenda, 5 p.m. Capital H is equal to H is KH. Does a higher or lower lambda value quickly stabilize the UMA control limits? Answer is higher. Could you explain, please? Yes. Okay. So that's the last exercise. Sorry, let me get back to where I was. Dig 6. It's getting late. Okay, so I did Q1, Q2. Consider a QSUM chart with NA greater than 1. Oh, this you can prove this. So unless there's question. Okay, I'm getting a little confused here. Do you want me to do question 2 on exercise 1? Anybody? Okay, if that's the case, I'm not looking at your questions right now because I'm getting a little confused. Does the UMA chart give more importance to every past observation compared to the current observation? So this is exercise 2. The answer is no. Weighted by lambda, right? So you give a certain weight to past as opposed to the current. Question 2, does a higher or lower value quickly stabilize? Yes. The reason it stabilizes is because if we remember the variance, the UMA was the mean, mu naught plus or minus L, and then you had sigma, and then we had an expression that is in the videos, and it had a oh, okay, I have this here. If you give me a minute. Okay, this is L square root of lambda over 2 minus lambda, 1 minus lambda to the 2I. Okay? So what this does graphically is it gives you sort of a limits that look something like that, okay? And then what happens is, so lambda is between 1 and 0, and therefore 1 minus lambda will be between 1 and 0, 0 and 1. Okay, so when you raise a value 1 minus lambda to the 2i, as I gets larger, as I goes to infinity, what's going to happen to 1 minus lambda to the 2i? What is going to happen to 1 minus lambda to the 2i? Anybody? Is anybody with me still, or are you answering each other's questions? It'll go to 0. Okay. So if it goes to 0, then this term will disappear. Now, from what values of lambda will it go to 0 faster? If lambda is high, then 1 minus lambda is small, and smaller will go to 0 faster. So therefore high lambda goes to 0 faster. So it stabilizes faster. Is that's the answer to does a high of Abdal Khan, does a higher, the Abdal, did I answer your question? Okay. Brenda, negative line in Minitab is not considered as an LCL. It is an LCL. Okay. So exercise 1, Q1 should be yes for Minitab then. Yes. What was it? Wasn't in control? No, I'm trying to keep track of. I can be bombastic. Exercise 1. Do CL and LCL for Houston chart depend on the sample size? Okay. So for Excel, the CL and LCL are 0, and so they don't. The question is, does UCL depend on the sample size? Okay, so tell me, Brenda, does the UCL depend on the sample size? Okay, and if that UCL depends on the sample size, then also the LCL. So for the Minitab version, you are correct. Okay. Now, just remind me, Brenda, what is the relationship between? Is it it's a table relationship? The n. Okay. Now there's still the lambda. Okay. There's lambda. Yeah. So now you might say what you have to do. What you have to do is you have to take what you're saying is you need to take the derivative of this function, this expression here with respect to lambda, right? You may need to do that because there's still lambda over 2. So you have to find out, does this expression here, does it go up or down with lambda? You can either do that experimentally with just going to Excel, or you can take the derivative. Maybe this part here, but this part doesn't depend on I. Sorry, this part does not depend on I. So if you break this up between this and that, this expression here, the only part that depends on I is this one here. So I think that that's still correct. So the higher the lambda is, this value will disappear faster than the other. Okay? It says the importance of the past data is decaying with time. Why is that? Yeah, because you give a value of lambda to the current one and 1 minus lambda to the old one, and that 1 minus lambda keeps on raising to greater and greater power. So the older values are reducing in influence on the value that you're accumulating. You're discounting older values, and every time you multiply by 1 minus lambda, they're losing their contribution. COP? Agree? It's because okay. Yeah, I think we're okay. I think I don't see any more questions, unanswered questions. Are there any more unanswered questions? Today is the last day, So this is the last office hour. There will be a piazza meeting with the TAs that do between 4 and 6 on Monday. So, and I'll also pop in and see what's happening on Piazza, see if I can straighten things out. But I got a ton of other things that I need to look after that have been sort of piled up because of this course. You will be getting an email as to the exact location, and that's it. It's 10 after 5 today. It was a pleasure. No more falls, and let me return just for a moment to where we were. Okay, and this should. Okay, Professor Francis, but you're welcome, and thank you. I don't know how to write it. Oh, here we go. Thank you. Okay, if it wouldn't be for you, I would be not learning all the wonderful things I'm learning. So it's a mutual thing. I wish you all the best, and hang in there, and that's it. Thank you. And I'm really glad that people were able to help each other, and that it's worked out. And thank you, Joanna and Allison, for making this possible. And we'll let you go now because it's late. Okay? Have a good time, and we'll be in touch. Take care.